In a small village there is one barber. He follows a single simple rule. He shaves everyone who does not shave himself, and he never touches anyone who does. Pick any villager and the rule fits perfectly. Only those who don't shave themselves come in. But there is exactly one person the rule can never answer for: the barber himself. In the early 1900s, this one-line question shook the foundations of mathematics. It was asked by the British philosopher and mathematician Bertrand Russell. So we call this Russell's paradox. There is almost no hard math in it. All you need is one thing: curiosity to follow what happens when something points at itself. Let's read the rule again slowly. The whole riddle turns on just two words. The barber shaves only the men who do not shave themselves, and he shaves all of them. The word all means every man who doesn't shave himself gets shaved, without exception. And the word only means anyone he shaves must be a man who doesn't shave himself. Now apply that rule to the barber himself. There are only two possible paths. Take the first path. Suppose the barber shaves himself. Then he is a man who shaves himself. But the rule says he shaves only men who don't shave themselves. Rule broken. Contradiction. Now the other way. If he doesn't shave himself, then he is a man who doesn't shave himself. But the barber must shave all such men. So he must shave himself. Another contradiction. Shave and he's wrong. Don't shave and he's wrong. There is no third way out. Both paths run down and stop at the same red contradiction box. So what's the answer? No need to agonize. The answer is disappointingly simple. Such a barber simply cannot exist. That's all there is to it. Think of the largest prime. It sounds fine, but primes never end, so no such number exists. Same with the round square. Perfect grammar, but nothing it points to exists. The barber's rule is the same. It contradicts itself, so no one can ever sit in that chair. Russell himself said this is no real paradox. And the barber costume wasn't his idea either. A contradiction shows up, you shrug, and it's over. We never believed in that barber anyway. But now the real question. What if the same trap appears and you can't say no such thing exists? Set the barber aside and become a librarian. A library holds a great many catalogs. Some catalogs list themselves as an entry. A catalog of all catalogs is itself a catalog. But a catalog of math books isn't a math book, so it doesn't list itself. Now the librarian makes one more. A master catalog of exactly those catalogs that don't list themselves. And then he asks, should this master catalog list its own name inside itself? If it does, it lists itself. But this catalog holds only the ones that don't. Contradiction. If not, it is a catalog that does not list itself, and all of those belong here. Contradiction again. It is the barber word for word. So mathematicians stripped off the costume and wrote it in its barest form. Split every set into two kinds. Normal sets which do not contain themselves and abnormal sets which do. The set of teacups is not itself a teacup, so it is normal. The set of all sets is itself a set, so it is abnormal. The set of all non-teacups is not a teacup either, so it quietly contains itself. Abnormal. Russell gathers every set that does not contain itself and calls it R. Does R contain itself? If R is inside itself, it must not be. If it is not, it must be. It is thrown out of both boxes. Why not just say no such set R exists the way we did with the barber? This is where it turns chilling. Back then mathematics had one assumption so obvious that nobody ever questioned it. If you can state a property clearly, you can gather everything satisfying it into a set. The set of red things, the set of prime numbers, the set of people over 180 centimeters tall, seemed as obvious as 1 plus 1. But not containing itself is just as clear a property. So by that assumption, the set R must exist. An object guaranteed to exist produced a contradiction. Deny that it exists and you deny the assumption itself. With the barber you can simply choose never to throw that rule. But the set's boomerang is tied to your wrist. As the philosopher Quine put it, we never believed in that barber, but we trusted this assumption like arithmetic. Giving up the barber is a yawn. Giving up this assumption was surgery on the foundations. Words alone make your head spin. So let's walk through it ourselves in 3 costumes one by one. The barber, the library catalog, the set are different costumes, exactly the same machine inside. A warm-up first. The empty set and the set of primes do not contain themselves, so both go in the normal box. The set of all ideas, on the other hand, is itself an idea. Abnormal box, no hesitation. But with our, whichever answer you pick, 3 lines later that answer flips. Saying no such thing exists is the only exit, and for our that door was shut. That shut door is our next stage. Turn the clock back to the late 19th century. Entirely new ground was opening up in mathematics. Once George Cantor tamed infinity with the idea of a set theory soon became the base language of mathematics. The man who set out to raise the grandest building on that foundation was the German logician Gottlob Frege. His dream was to prove all of arithmetic down to why 1 + 1 is 2 from the laws of logic alone. That life's work is his 2-volume masterpiece, The Grundgesetze der Arithmetik, The Basic Laws of Arithmetic. One cornerstone of that vast building was that very assumption. Write down a property and a set appears. On June 16, 1902, a young and almost unknown Russell sent Frege a letter. A polite greeting, then the paradox of R in just a few lines. Volume 2 was being finished at the printer right at that moment. Frege recorded the shock at the end of Volume 2. At the very moment his work was finished. Nothing more unfortunate can befall a writer than to have a foundation of his edifice shaken. Mr. Russell's letter put me in exactly that position. Zermelo too found the same contradiction on his own around 1902 and buried it, and Russell hid it while digging into Cantor's proof about infinity. In fact, Russell's paradox was never alone. Whenever something points at itself and a knot slips in, the very same contradiction is born. Self-reference loads the gun and the word not pulls the trigger. The oldest relative is the liar paradox. One single sentence. This sentence is false. If it is true, then just as it says, it is false. If it is false, it turns out true. Cousins include Berry's paradox and the Grelling-Nelson paradox, which asks whether a word describes itself. Russell's question is, are a member of R and the liar are really the same machine? Pin it as true and it turns false. Pin it as false and it turns true. The truth value flickers forever, never settling. The fascinating part. Someone used this machine for creation, not destruction. That was Kurt Gödel. In any powerful enough logical system, there must be statements that are true but unprovable. That was the engine of paradox. Now back to that collapsed foundation. The real culprit was not the barber, not the catalog, not even the set R. The culprit was that loose assumption. Just name a property and anything becomes a set. So they rewrote not the barber, but the constitution of sets itself. That is today's standard ZFC. The key prescription came in 1908. Zermelo's axiom of separation. The idea is surprisingly modest. Do not scrape everything together at once out of nothing. Only pick things out from a set you already hold. You cannot summon the set R out of thin air. You can only carve it out of some set A that already exists. Then putting every set into one basket becomes impossible. Instead, that no universal set exists is proved as a theorem. The material for building R is gone. There is also the axiom of regularity, which forbids self-reference, but the real hero is separation. Russell's other prescription was type theory. Every object gets a level, and members may sit only one level below. Then saying a set contains itself as a member is not false. It is ungrammatical to begin with. This sorting into levels later flowed into computing, and it still guards someone's code today. A question that began with a small-town barber made mathematics rebuild the ground it had stood on for over 100 years. 3 lessons are left in our hands. Once a knot slips into self-reference, a rule trips over its own feet. An imaginary barber you can simply erase, but a set whose existence was guaranteed you cannot. The spot mathematicians finally repaired was exactly where the problem began. The cure points to the culprit. Self-reference, the poison that nearly toppled mathematics, became in the right hands the medicine that yields the deepest theorems. Sometimes the silliest-looking question tells us most honestly how thin the ground beneath our feet really is. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. See you in the next story.